today, Mr. Jason Dane is going to talk about the relatively hyperbolic Dane filling theorem.
All right, great. Thanks for coming again. Let's see. Need some white chalk. Okay. All right, so last time we kind of introduced so the definition of relatively hyperbolic groups and gave some examples. So today I want to connect that to Dane filling. So I'm going to use a result I mentioned the last time, this result of Bowditch. So, which was that if I have G hyperbolic, and if I have P a subgroup of G, so then the pair GP is relatively hyperbolic if and only if P is quasi-convex and almost null-normal. Okay, so if you assume that G is torsion-free, so we get the following corollary. Actually, this is true even if G is not torsion-free. So let me just state it as follows. So suppose that alpha is in G hyperbolic, and suppose alpha is not a proper power. So if alpha is not a proper power, then in particular it can't be a torsion element, right? So it's going to be, if I think about its action on the, oh hey Sam, sorry we started early. So if you think about its action on the Kähler graph of G, then it's going to act hyperbolically, right? So orbit is going to be a quasi-line, quasi-isometrically embedded line. So in particular it's going to be quasi-convex, and you can show, and let's actually just suppose that G is also torsion-free. So that the following is true. So then the cyclic group generated by alpha will actually be male normal, and so then Bowditch's theorem will tell you that that G is hyperbolic relative to that cyclic group. So then G cyclic group generated by alpha is a relatively hyperbolic pair. Now what to do if there is torsion? Well, alpha lies in some maximal virtually cyclic subgroup, and I would need to replace the subgroup generated by alpha replace it by that. But this is enough for what I want to talk about. So I want to talk about understanding what is the classical hyperbolic Dane surgery theorem in these terms. So classical Dane filling, and what I mean is Thurston's hyperbolic Dane surgery theorem So we're going to start with this hyperbolic three-manifold. So this is supposed to be a hyperbolic in the sense of differential geometry, three-manifold with this cusp C, which is homotopy equivalent. Assume it's homotopy equivalent to a torus, so it's just torus cross 0 to infinity. So on the level of groups, I have this group pair pi1 of M, pi1 of C, where this pi1 of C looks like, say, Z plus Z. I Dane fill. And now I'm going to get this, I'm going to draw the same picture that I keep drawing. So M minus C, union the solid torus. I'm going to glue that solid torus so that its meridian goes to some curve here, geodesic in the boundary, gamma. So this is M gamma. And we're assuming that, so anyway, so if I just think about on the level of groups, what's happened, I've attached a relation. So I've got this pi1 of M gamma, and then comma something. Well, it's the image. So if this is some map phi, it's the image of pi1 of C. Okay. Now, if the length of gamma, so this is the hyperbolic Dane surgery theorem, which I'll just write HDST for short. If the length of gamma is long enough M gamma is compact hyperbolic. So hence what? Well, the fundamental group of M gamma is acting properly co-compactly on H3. That's a delta hyperbolic space. So it says that pi1 of M gamma is a hyperbolic group. So this hyperbolic means hyperbolic as a manifold, and this hyperbolic means hyperbolic as a group. Right? So, moreover, if I think about the core of this solid torus, that's going to be isotopic to a simple closed geodesic. So this core, we'll call it alpha. Moreover, the core 0 cross S1 sitting inside the disk cross S1 is homotopic in this metric to a simple closed geodesic. Okay, if it's homotopic to a simple closed geodesic, that means it's not a proper power, right? If it was a proper power, it would wrap around that geodesic a bunch of times. And so that tells you that the pair, and moreover, it tells you that this is isomorphic to Z in that case, assuming the gamma is long enough. So the pair pi1 of M gamma, comma, subgroup generated by alpha. So this is also relatively hyperbolic by Bowditch. Okay. So the way of understanding Dane filling on the level of groups, as you started with a relatively hyperbolic pair, you did some operation where you attached a relation to the boundary and you got a new relatively hyperbolic pair nearly all the time. So for generic gamma, you get a new relatively hyperbolic pair. Okay, so hopefully that will make what I'm about to write down a little clearer, which is going to be the group theoretic Dane filling theorem. Okay. Set up a little notation first. So this is Dane filling of spaces. I want to talk now about Dane filling of groups. So we're just going to let GP be a group pair.
I'm sorry, so
yeah.
if we move on, so alpha is not uniquely determined by gamma. So
it is.
You don't know where it goes, right? Because there are multiple. So if you
it's
gamma,
yeah.
There are several ways of gluing the boundary.
There's several ways of gluing the boundary, but they're all related by a homeomorphism of the solid torus that fixes the core. That fixes every point in the core, yeah. So the only thing you could do is you can kind of twist the solid torus along its that disk. I guess you could reflect it or something, but then again, that's going to preserve alpha. So that might change the sign. So it might change alpha to alpha inverse or something. But we were just really interested in the cyclic group generated by alpha. So, other questions about this picture that I'm about to obfuscate with group theory? Okay. All right. So we've got GP, a group pair, and I want to say what's a filling of that. So we're going to choose N, a normal subgroup of P, and then a Dane filling. Oh, sorry. Let me say it this way. So, okay. Let me just say it this way. So I've got N, a normal subgroup of P determines a Dane filling. Something I'm going to call a Dane filling, and everything I call a Dane filling from now is something like this. So, and what is it going to be? So it's going to look like G of N phi N of P, where G of N is just defined to be, well, I take G, and then I mod out by the normal closure of N in G. Right? So N was normal in P. That doesn't make it normal in G. In fact, P is almost malnormal in G. So N is going to be almost malnormal as well. Well, not almost malnormal, but it's going to have lots of conjugates that are different from it. So G of N is that, and if I look at G to G of N, this is just the filling map. Which just takes, it does the obvious thing. G goes to, the coset of the normal closure of N in G. But I want to be able to refer to that map. So that's a Dane filling. That's the definition of a Dane filling. And now you see that generalizes what's happening here because I'm attaching this peripheral relation. So you want to think of N as composed of all the new peripheral relations that I'm going to add to the group. So, okay, so the relatively hyperbolic Dane filling theorem. Which is due to Ozen. There's also a paper of a couple papers of Daniel Groves and myself, independent, which give a proof in the case where there's no torsion, and which can be extended to the case where there is torsion, but that doesn't appear in the literature, and then there's a recent paper of Damani, Uridel, and Ozen giving a much more general theorem than the theorem I'm about to state. I think I will tell you in a little bit what that is, but let me focus on the Ozen's version of the relatively hyperbolic Dane filling theorem right now. So we're going to let G P be a relatively hyperbolic pair. And let F in G be any finite set. So then there is a set B, a finite set B, for bad. So these are the bad things. So B in the three-manifold setting you want to think of as composed of the short loops on the boundary torus. So there's a finite set B, so that if n, so we're going to put B inside P minus the identity, and we want to say that n intersect B is the empty set. Then, so in general, what do you have here? So if I think about phi sub n restricted to P, so I get phi sub n of P over here, that's certainly going to factor through P mod n, right? Now, it may or may not be the case that this second map is injective. So that's the first conclusion here, is that that second map is injective. So I'll just write that as phi n of P is equal to P mod n, where I'm making a sort of, hopefully you can interpret that so that it's correct. So so I mean that if I look at this map here, then that's an isomorphism. So second is that phi sub n restricted to F is 1 to 1. And then 3, if I look at the pair G of n comma P mod n, this is relatively hyperbolic. Okay, so we're kind of recovering sort of some of the group theoretic content. Now the significance of this second statement will maybe not be so clear until later. But what you can see the first and the third statement are very much like what we said happened in the three-manifold case, right? So what was left of the peripheral subgroup was exactly the cyclic group that came from the core. And that was Z plus Z mod out the curve bounding the disk, right? And then this bottom part was what we just talked about here, was that pair is still relatively hyperbolic. And let me kind of put a little addendum here for, moreover, if S was a... So remember, we built this cusp space. We talked about this cusp space yesterday that was built from the pair G comma P with respect to a certain generating set S for G, right? So fixing a generating set S for for G so that P is generated by S intersect P. So if so we know that X of GP S is delta hyperbolic for some delta. So let's just pick a delta for which it's delta hyperbolic. So then if I look at X of G of N, P mod N, and then with respect to this same generating set, this is 300 delta hyperbolic. Now the 300 delta is really probably 4 delta, but the things I'm going to quote today get you 300 delta. Okay. The important thing about this last part is that the hyperbolicity of this cusp space for the quotient is independent of n. Independent of n. So I can build. I can look at a. Well, we'll talk about why that's important later. Are there any questions about this statement before I say anything else?
So where is the corresponding statement to the fact that pion of m gamma was hyperbolic?
That's the fact that this pair is relatively hyperbolic. So no, yeah. So this is something I should have said, but I didn't. Which is that if I have a pair GP is relatively hyperbolic and P is hyperbolic, then G is hyperbolic. So in the three-manifold setting, this was the integers. So the second term was hyperbolic, and so that's going to imply that this is hyperbolic as well, that the quotient is hyperbolic. Yeah, that's a good question.
So in number 2, 1-to-1 means they are just distinct. The
Yeah.
each of them are distinct.
That's right. So yeah.
Some are allowed to go to say trivial element. So it doesn't matter.
Well, it doesn't matter. But if you don't want that to happen, then enlarge F so that it contains the trivial element. Yeah. So that you should think that you're preserving as much finite, as large a finite amount of the multiplication table as you want. Right? So, yeah, that's the right way to think about it. And in terms of well, let me say something about that. Actually, let me say something about 2. So just some kind of immediate consequences. So one is what we've just been talking about is so much of the group theoretic content of the hyperbolic Dane surgery theorem, the 2-pi theorem, etc. So a lot of it, not all of it, but quite a bit of it. Second, though, has to do with this this business of being able to choose B so that the Dane filling is injective on big sets. So if P has lots of normal subgroups, this is saying that I can approximate G by its Dane fillings. Say if P is residually finite, for example. and then G is fully residually hyperbolic. So P really could just be fully residually hyperbolic. Or I mean that down there. So what does fully residually hyperbolic mean? So it means that given any f finite in G, there exists a hyperbolic quotient G bar, and I've got a phi from G to G bar, so phi restricted to f is injective. Okay. Point is that finite groups are hyperbolic for sort of trivial reasons. There's a bound to how big of a triangle you can make in a finite graph. And so if this group P is residually finite, then it means it has a nested sequence of finite index subgroups. And I can Dane fill along those subgroups. Those subgroups will eventually miss B for my favorite finite set F. And so they'll eventually, the quotient maps will all be injective on F. So one way you can think about this is in terms of the space of marked groups. If I fix a number of generators, I can think about all the possible Cayley graphs of groups with that many generators. And it's saying that this G comma P is in the, so right, and I can put a topology on there. I can put the sort of topology of a convergent sequence is a sequence where larger and larger balls around the identity look the same, right? And so, or stabilize, right? And so this is saying that a relatively hyperbolic group with a residually finite or a fully residually hyperbolic peripheral structure is actually a limit point of the set of hyperbolic groups in the topology of marked groups in a fixed number of generators. Okay, and then maybe I'll mention a third thing that I'll talk about much more next time. Three. So there's many applications to separability of quasi-convex subgroups. So CF Tuesday's lecture. So I'll talk about some of that the next time. Okay. I also want to talk about some generalizations of this theorem. So, in fact, in Ozen's original paper, he actually proved a slightly more general result than this, but which you can actually get fairly easily from the result that I wrote down. So, and it's the following: is that so there's a notion of relatively hyperbolic pairs, where the second group, where the groups are not required to be finitely generated. So the way we define the cusp space, they needed to be finitely generated because I wanted a finite generating set for G that contained a finite generating set for P. Okay, that's actually not necessary. And there's a nice paper by Chris Ruska sort of explaining how you can generalize, how you can think about different ways of thinking about infinitely generated relatively hyperbolic groups. So we can generalize actually fairly easily to infinitely generated groups. G, P. And this has some very interesting consequences. So Ozin, again, uses this to construct some very exotic groups. So, for example, given, say, a torsion-free group, everything's been G so far. Maybe I'll say A. He can construct a two-generated G with A embedding in G, and it has precisely two conjugacy classes. So there's the conjugacy class of the identity and the conjugacy class of everything else. Right? So it was an open question for a long time whether there existed any such finitely generated group besides Z mod 2. And so Dennis showed that you can embed any group at all into such a group, any countable group, any countable torsion-free group. And so he has some other result about if there's torsion, so that you can get as few conjugacy classes as possible. The set of conjugacy classes is the set of orders of elements. Yeah?
So what was written in front of
TF, which is supposed to stand for torsion-free. Yeah. So much more recently, I mentioned Damani, Giradel, and Ozin generalize the statement to pairs G, P, where P is so-called hyperbolically embedded in G. And I think it's maybe worth just talking about what the definition of being hyperbolically embedded is, because it's related to an alternate definition of relative hyperbolicity, the kind of relative hyperbolicity I've been talking about. So here's an alternate definition of GP being relatively hyperbolic. So again, we're going to choose S a generating set, say it's for now a finite generating set, for G, and now I can make this graph called C of G, comma P, comma S, as follows. So is the graph with a vertex set equal to G disjoint union left cosets of P, and then two types of edges. So the first type is the type that you see in a Cayley graph. So G is going to be connected to GS for G and G S in the generating set. By the way, this picture is basically due to Bowditch. This point of view is related to points of view of Bowditch and to Farb. So it comes early in the study of these things. And then the second type of edge, so that's the first type of edge. And then the second type of edge is we're going to connect G to, so G to GP for any G in G. Okay, so how do you want to think about this? So a good way to think about this is I've started with a Cayley graph of G, and now for each left coset of P, I've taken the vertices corresponding to that left coset and just coned them off to a point. So sort of added a bunch of cone points to the left cosets of P. Okay, so now, so here's the definition of relative hyperbolicity is one, this graph C of G, P, S should be delta hyperbolic for some delta. And two, if I look at removing the vertex corresponding to P, so what is the picture here? Let me draw a picture before I write this down. Do some colored chalk. So whatever, I've got this sort of Cayley graph, and maybe I have the vertices of P, and I'm kind of coning them all off to this vertex labeled by P. Okay, let's call that V of P. And then over here, maybe I have some other vertex corresponding to, so that's V of GP for some G. So what I can do is I can remove this vertex V of P, and then I can look at what the metric is on P. So that's these vertices here that have been coned there. And I want that to be locally finite metric. That's all. The metric on C of GPS minus the vertex corresponding to P restricts to a locally finite metric. I guess I was calling this proper before. It's the same thing. Proper metric on P. Since P is a discrete set, it's the same thing to say that the metric is proper as to say it's locally finite. So I just mean that if I look at a single vertex of P and look at all the vertices of distance at most R from P, that should be some finite set. Which is not the case before I remove V of P, right? Because all of P is within distance 2 of this vertex. But now, if I remove it, then I should get something locally finite. Okay, so that's an alternate definition of relative hyperbolicity. It's not at all clear why this should be the same as the one that I gave before about this cusp space. But in fact it is. So this coned space being delta hyperbolic plus this extra condition is equivalent to the cusped off space being relatively hyperbolic. being Gromov hyperbolic. Now, what does it mean? Yeah.
Is that graph quasi-isometric to the graph defined yesterday?
No, it's very different. It's a very different graph. Yeah, that's a very good question. Yeah, so this graph, because I've kind of taken all the so you can get this graph from the graph yesterday by taking each of the horoballs and then at depth 1 and below, just take that whole horoball and shrink it to a point. All right? So that horoball had a limit point at infinity before, and now it's gone. So I've distorted the boundary horribly. Yeah. And in fact, So the graph I described yesterday is a proper delta hyperbolic space, which is going to mean that its boundary at infinity, which I didn't define, but maybe you've heard of before, is compact. And this thing is almost the boundary at infinity of this space is almost never going to be compact. So in some ways, this is a much nastier space, I think. I mean, and the group doesn't act properly on it anymore either, because P is going to, so P is probably this infinite group, and it's all going to fix this point. So the action is no longer proper. So yeah, it's a very different space, but they're kind of closely related. You can kind of, Bowditch kind of tells you how to get between them in a kind of cute way. Yeah, so I mean, and the way you can think about it is you can think about putting a little triangle in here for each, say you were in the situation we talked about yesterday where S contained a generating set for P. Then there's this whole Kähler of P up here. And I can cone that Kähler to a point. Now I get a bunch of triangles. I can replace each of those triangles by a hyperbolic spike. So a hyperbolic spike, if this is H2, I look at this subset. Right? So that's a kind of a triangle with two real vertices and one ideal vertex. So if I replace each of those with a spike, I'll get something quasi-isometric to the space I described yesterday. That's how you go back the other way. All right. Other questions about that? Okay, so
Fully finite means every ball centered at an element of P has finitely many elements.
Exactly.
So what if what if some element belongs to GP and P? So
well, GP and P are disjoint. But it could belong to the, yeah, if like to P and to the conjugate of P by G. Yeah. If there's an infinite order element there, then it's not going to be relatively hyperbolic, right? You're going to get this picture of this sort of doubled horodisk embedding in the cusp space that I defined before.
I'm just mistaken. Yeah. The picture looks like GP and P intersect. The blue here.
Oh yeah, they don't. It's a lie. I'm sorry. Yeah, that's a lie. They coarsely maybe intersect in a bounded set. Yeah. Okay. Right. Oh, okay. So what does it mean for P to be hyperbolically embedded? It's the same condition, but you drop this condition that S is finite. You're allowed to choose S to be an infinite generating set. So if 1 and 2, meaning this 1 and this 2, are satisfied for some not necessarily finite generating set S, then we say that P is hyperbolically embedded. Okay. And that's the context to which Domani, Girardelli, and Ozin are able to extend the Dane filling theorem. And that has, that extension has applications, has some interesting applications to mapping class groups, to something called the Cremona group, and just all kinds of other exciting stuff. But I'm not going to talk about this more general condition anymore beyond what I've done right now. Okay. All right. So that's what I wanted to say about generalizations. And I think this is about as far as it generalizes. So my plan for the rest was to give you some kind of hand-wavy sketch of the proof of the Dane filling theorem that I wrote down before. So maybe I'll just write in shorthand. So the relatively hyperbolic Dane filling theorem is going to say that I've got G comma P, relatively hyperbolic. I've got F, finite, sitting inside G. So then there exists a bad set B. So if N intersect B is empty, so and B misses the identity, so N intersect B is empty, then we get these nice consequences. So one was that P mod N embeds into G. Two was that F embeds into G. And then three was that the pair G P mod N is relatively hyperbolic. Okay. So just so we don't totally lose track, I'll try and leave that up there. All right. So that's what we're going for. Now I wanted to, and there was also this statement about delta being independent. So let me talk first about 3. How you're going to get. So I want to sketch of a proof of this theorem. So this is not a proof. This is not the proof that's written down in any of the papers about this exactly. It's a sort of combination of different proofs and has something to do with the proof that I'll write down if I ever write a book. But it goes kind of like this. So first of all, we want to show these things. We want to show that.
By the way, do we have to write G and
Yeah, G of N. Sorry. Thank you. G of N, G of N, G of N. Okay. Thank you. Yeah. Right. Other. Yeah. Thank you. So, assuming 1 and 2, one way to get 3 is something called the Course-Cartan-Hadamard theorem. Which I think is basically, well, Gromov certainly knew that this was true. So Gromov, but I should also say you should see Papasoglu, Delzant, Gromov, and some notes of Remy Coulon are probably the best, might be the best place to learn about this if you're interested, which you can get from his webpage, I think. So what does it say? So it says, I'm going to write down some terms and then define them. So suppose X is a geodesic metric space which is sigma locally delta hyperbolic and 10 to the minus 5 sigma simply connected, where sigma is at least maybe I should say bigger than 10 to the 7th times delta. Okay, then x is delta hyperbolic, or is 300 delta hyperbolic. So it's saying, much as the Riemannian geometry version of Cartan-Hadamard says that says what? It says if I have a manifold of non-positive curvature and I look at its universal cover, then that's Rn, right? So it's saying that I can take this local geometry and I can get, in the universal cover at least, this global geometry. And the CAD0 version says that I can take a local CAD0 condition and get a global CAD0 condition on the universal cover. So here I don't want to pass to a universal cover. I want to make this assumption of large scale or medium scale simple connectivity, which is going to mean that X is sort of its own universal cover, at least as seen from that scale. And so I want to say that this local negative curvature implies a global negative curvature. So let me give the definitions. So one, X is sigma locally delta hyperbolic if every ball of radius sigma is delta hyperbolic. So if I take the ball of radius sigma around X, this should be delta hyperbolic. For all X in big X. So I'm fixing delta, right? And sigma is much, much bigger than delta. So it is a non-empty statement to say that this bounded metric space is delta hyperbolic, right? So bounded metric space of radius r is always r hyperbolic, but this is saying something more. It's saying it looks like a little piece of a big delta hyperbolic thing, maybe. And so that's the local thing. And then what does this mean, simply connected? So X is alpha simply connected if the fundamental group of X is generated by loops freely homotopic to maybe other loops of diameter less than or equal to alpha. It's just saying the fundamental group is generated by short loops. Okay. I have to use free homotopies because these short loops might be super far away from my base point, right? And they might be arbitrarily far away from the base point. Okay, so for example, if you take the Cayley graph of a finitely presented group, it's going to be alpha simply connected for alpha equal to the length of the longest relator in your finite set of relators. Right? So it looks simply connected on the appropriate scale. And the hypothesis here is that you look delta hyperbolic on a scale which is at least 100 times as big as the scale on which you're simply connected. Okay, so it's saying that, yeah. And another way of thinking about this, if you know about the characterization of hypervelocity in terms of isoparametric inequalities, if you don't worry about it. Let me just say a sentence about it. this is, so it's a result again of Gromov, there's a proof by Papasoglu that says that if you have a group that is that sort of looks like it has a linear isoparametric inequality on big enough scales, then it has a global linear isoparametric inequality. So there's also proof of this very general setting by Bowditch. Sort of just subquadratic is actually enough to get, on big enough scales, is enough to get you linear isoparametric inequality. The point being, for those of you who haven't heard these words before, having a linear isoparametric inequality is another equivalent condition to being Gromov hyperbolic. So, and if you're not a simply connected space, then you want to just say, well, if you're alpha simply connected, what do you mean by having a linear, any kind of isoparametric inequality? You mean you're going to think about killing off with disks all the loops of length less than alpha, or diameter less than alpha, and then measuring it. Something like that. Okay, so now, once I have these things, I claim that the Coarse-Cartan-Hadamard theorem is going to give me the theorem. So CCHT implying plus 1 and 2 implying number 3. So how is that going to work? Well, I need to show that the cusp space for G of n comma P mod n is delta hyperbolic for some delta. So I want to show x of G of n comma P mod n is 300 delta hyperbolic. Now, by appropriate choice of n, I can ensure that right. Well, let me say it this way. So there's a quotient map. So if I think about this x of G P, I can act on that by the kernel of phi n, and the orbit map is basically going to be x of G of n P mod n. This is assuming that I have that first part, that P mod n is embedding in G mod n, right? So that P mod n is actually a subgroup of G of n. All right. So this is the orbit map. So now, if I can make any finite set persist, if I can make it miss the kernel, then what that is going to mean is that I can make this map injective on a very large ball around the identity, right? Not necessarily on a very large ball around a vertex of very big depth, but I can make it injective on a big ball around the identity. So choosing B appropriately. So let me give this map a name. Let's call it pi. Can ensure pi restricted to a large, so say how large? I want it to be, say, a 2 sigma ball centered on 1 is injective. Okay, so that tells me that if I look close to the Cayley graph in the target, then I look at a sigma ball centered at a point within sigma of the Cayley graph here, then it's going to look exactly like a sigma ball here. And everything here is delta hyperbolic. So that gets you the local hyperbolicity near the Cayley graph here. So this gives you sigma local hyperbolicity, local delta hyperbolicity within delta of the Cayley graph of G of n. Okay. But now, if I'm not within sigma of the Cayley graph of G of n, that means I'm deep inside one of the horoballs, one of the combinatorial horoballs. And there, everything looks 10 hyperbolic. So, for the distance between x and the Cayley graph of G of n bigger than sigma, the sigma ball about x lies completely inside the horoball based on p mod n. And this is 10 hyperbolic by the exercise from last time. Okay, so that says that x of G of n comma p mod n is sigma locally, well, technically it's the max of delta and 10 hyperbolic. But I can assume to begin with that my delta was a zillion, so it's bigger than 10. So the max of 10 in delta is delta. Okay, so that gets you the first condition. That gets you sigma locally delta hyperbolic in the quotient. So I used both of these here, right? So I used that the peripheral subgroup was embedding as much as it could, and I used that I could embed a large ball in the group into the quotient, right? And embedding that large ball in the group, it's not, you have to think about it for a bit, but that is going to tell you that you actually embed a large ball of the cusp space in the quotient cusp space. I didn't really say why that was, though. Okay, and so now what do we need? We need this simple connectivity. So what about the Cayley graph? Sorry, what about the fundamental group? I1 of the space x of G of n comma p mod n. So what are the loops I need to generate that? Well, so there's a fact of Ozen. So he shows that if G comma P is relatively hyperbolic, then G is finitely presented relative to P. Okay, so we said before, I was talking about what kinds of Cayley graphs are something simply connected, right? It's exactly the Cayley graphs of finitely presented groups, right? Now G might not be finitely presented, but if it's not, that lack of finite presentation comes from P, right? And so if I think about a big loop in P, I can push that down into the horoball and get a small loop, okay? Not by a homotopy, but by sliding across squares, right? So remember that what does the horoball look like? I've got my edge here at some level. I have vertical things here. If things were connected up here, they're still connected down here. So I can take a loop and I can slide it down until it becomes very small diameter, right? So, so this implies that that what? That the space G of n P mod n is, well, it says about the x of GP is going to be R simply connected for some R. But in fact, it's not hard to see that this space is also going to be R simply connected. So when I wrote, is R simply connected for R independent of N. Okay, so I need to go back and choose sigma, re-choose sigma. So I should have chosen sigma to begin with, so that it was bigger than 10 to the 5th times R, right? So if sigma is bigger than 10 to the 5th times R, then I'm going to get that this quotient space here is still is 10 to the minus 5th times sigma simply connected, and then I'll be able to apply the Course-Cartan-Hadamard theorem. I got both conditions, and I'll be able to deduce that that space is 300 delta hyperbolic, right? So once I have 300 delta hyperbolicity for this space, well, that was the definition I gave of the pair being relatively hyperbolic. So that tells you that this pair here is a relatively hyperbolic pair. Okay, so that's one way to prove the third fact from the first two facts. Questions about that? I should stop soon. Okay, let me say a few words about the first two, and here I'm going to lie vigorously. Okay, so how do you prove 1 and 2? So for 1 and 2, so this is the idea behind a proof of 1 and 2. So there are other ways to attack this problem. So pretend that G is equal to the fundamental group of a one-cusped hyperbolic manifold. And that P is equal to the fundamental group of its cusp. Okay. So now I have this picture of M with a cusp, and now I have this set F, which I can break up into two parts. So Q1 up through. Oh, and let me just point out that we're going to buy a trick. So let me remark. Phi n restricted to F injective is the same as saying that if I look at phi n, saying that the kernel of phi n intersect FF inverse is a trivial element. So it's just saying I haven't identified anything in F. So what I'm really going to do is I'm going to take F and I'm going to try and show that its intersection with the kernel is trivial. So show F intersect kernel of phi is equal to 1. Okay. For appropriate choice of n. Right? For appropriate choice of set that we want to avoid B. Okay, so now, does everybody understand the way I've sort of rephrased the question? Instead of looking to be injective on this set, I'm going to consider its intersection with the kernel. And, okay. All right, so F divides up into some parabolics and some hyperbolics. So there's some Q1 up through QK, and these are parabolics. And then some hyperbolics. H1 up through HL, hyperbolic elements. Now, what's true about hyperbolic elements of isometries of hyperbolic space is they have nice axes. So something similar is true about hyperbolic elements acting on the cusp space, but certainly true about elements acting on hyperbolic space. And so that I can look at the axis and then mod out the action of everything. I'm going to get some loops in here. All right. So some finite collection of loops. So H1, H2, H3, H4. That's some compact set. So I can choose my cusp so that they all lie on the compact side of it. So I'm going to choose the cusp C so that geodesic representatives for H1 up through HL lie outside C. C. So we may assume that Q1 up through QK are actually in P, right? So to say that they're parabolic just means that they're conjugate into P. But I may as well go ahead and conjugate them into P. So if I don't want them to lie, so if a conjugate of something lies in the kernel, then that something lies in the kernel. So asking to keep them out of the kernel is the same thing either way. So now we're going to let B sitting inside P be so contain those Q1 up through QK, as well as all elements with representatives in the free homotopy class on boundary of C of length less than 2 pi. So what I'm really showing you here is this sort of part of the proof of something called the Six Theorem, weakened so that 6 turns into 2 pi. So I'm throwing out all the short elements on this boundary torus, and I'm throwing out these specified parabolic elements as well. So now, what I want to do is I want to suppose. Sorry, I'm going over a couple minutes. Is it okay if I go over for a couple minutes, or should I stop and let people leave? Okay. Yeah. Okay. Hopefully this won't take too long. So, okay, what do I want to do? So suppose I have, so P 0 is in the kernel of phi n restricted to P minus n. And suppose it's the shortest. Among such elements. So then, to say that it's in the kernel means that P0 is equal to a product, I going from 1 to k, of conjugates, gi n sub I GI inverse, or the n sub I are all in N. So they're all not in B, right? They're non-trivial, not in B. And I want to choose the shortest such representation. So we're going to choose K, also minimal. Now that equation has a geometric interpretation. So as follows, so I can think of it as I've got P0 over here, and there's a kind of surface like this. So where this is N1, N2, all the way down to NK. Now this surface maps in somehow to here. So maybe I should give it a color and make it blue. So I've got this bunch of loops here, and then there's this surface that's kind of somehow in here like this, right? So I can take those boundary loops and I can extend them into the cusp, and I'll get a map of a punctured surface. A proper map of a punctured surface into this manifold M. And now I can triangulate that with an ideal triangulation. Sorry, I drew an extra edge there. Okay. So ideally triangulate the relation and pleat it. Okay, if I pleat it, that means I'm going to replace each of these triangles by an ideal hyperbolic triangle with geodesic edges. So geodesic edges going from the cusp into here, wrapping around somewhere, and then going back out the cusp. Right? Now these minimality conditions ensure that I can do that. So use minimality. And then I just think about the area of this triangle. The area of the surface. So the area of the surface is at most 2n minus 2 times the area of a hyperbolic ideal triangle, right? I mean, it's equal to that, isn't it? On the other hand, these loops have some length. Right, and they have some bound from below on that length, and that gives you a lower bound on the area of the part of the surface that's in the cusp. So the area of the surface is at least n times, so the sum I going from 1 to k. Sorry, this should be a k. Very confusing. Yes, that's a k. The sum as I goes from 1 to k of the length of the ni measured as a geodesic in the boundary torus. And of course this is bigger than or equal to 2 pi times k. And that's a contradiction. Okay. This is the geometric idea underlying a proof of this first part, that P mod n goes into G mod n, into G of n. And this comes from a paper of Mark Lackenby. So this is sort of a Lackenby proof. So CF, Lackenby's proof of the Six Theorem. All right. And I will just say that ensuring the second condition is very similar. So instead of having a surface with just punctures, you're going to have a surface with geodesic boundary equal to one of these yellow guys. And you're going to make a very similar area estimate and get the same contradiction. So you get the same contradiction, which says that, which tells you these two conditions hold, and then you can use course Cartan Hadamard to get the third condition. And I should probably, I'm way over time, so I should stop.